Cool, thank you. So welcome everyone. Great that so many people are interested in today's topic, from Serverful to Serverless Java. My name is Maximilian Schellhorn. I'm a senior solutions architect with AWS, and this is my colleague Dennis Kieselhorst. We will switch between the different sections, so Dennis will come on later and tell you a bit about events. Cool. So what we've been doing, so over the last couple of years, we've been working with a lot of customers and companies and help them modernizing their Java applications. And serverless is an integral part of that journey. So we gathered a lot of best practices and workshops, also reusable workshops that you can do afterwards. And we want to share a little bit the common paradigm shift that we see when you move from a more like a traditional server-based application to a serverful environment. So to understand why and what this is about, we will first look at a traditional Java application that you probably very commonly see out in the wild. So usually you have some form of load balancer as an entry point to your application, and then after that you have like a scalable target. So multiple instances of containers or VMs, and the load balancer is distributing that load to those servers or VMs, containers, whatever. And inside of those containers, we usually have our things like an HTTP server, so things like Tomcat. We have our framework that we use, Quarkus, Micronaut, Spring, for example, and our application code. And I think this is production proof, and probably a lot of you are doing something or a variation of this already today. But it also has a couple of implications that we kind of just accept by default. So one that I want to highlight is usually those resources, if they are server-based, they are running 24/7. So think about an HTTP server and the backend and the load balancer. You really need to pay 24/7 for them, even if you're not receiving any kind of traffic, right? So they are just there. Usually they're even in high availability, so you not only pay for them once, but actually twice, regardless if you get requests or not. The second one is that in containers as well as VMs, we are dealing with a very coarse granular way of scaling. So that means, let's say my Spring Boot application is capable of handling 100 concurrent requests in a single container instance. If I get the 101st request, usually I would spin up a second container just to accommodate that one additional request. It will stay there. After some time, we will scale down. But it's like a very coarse granular way of scaling. And last but not least, there's a lot of maintenance involved. So depending on the abstraction that you choose, if I go with VMs or containers, right, I need to patch the underlying operating system, or I need to update the base images. I need to ensure that everything runs in a highly available fashion. So the maintenance effort is quite high for a very standard application that we use every day. And the question I want to ask you is, can we do things differently? So what would be aspects that would make our lives easier? And can serverless help us here, like somehow? And I would like to explore that by looking at the four main characteristics that we would expect from a serverless system. So the first one is reduced operational overhead. So ideally from a serverless system, I would expect that I don't have to upgrade or maintain any kind of servers, or I need to patch anything. And usually also I want to have high availability by design. So that means if I run my code in a serverless fashion, it should be automatically distributed across multiple data centers in case there's an outage or something affecting. I want the service to ensure that it's running very smoothly without needing to know about any of the details. The second one is I want automatic scaling, and that I want of the unit of consumption. So that means rather than scaling on a server unit or based on CPU or memory, I want to actually scale on the most fine granular way possible. So for example, on a specific requests. So I only want to scale a new serverless instance, for example, if I get one new request, okay? And that directly relates to paying for value. So if I only spin up the resources that I need in a very fine granular fashion, then I will also expect that I'm only paying for that duration or the work that I'm doing. So that can be I only pay for the number of requests, for example, or the gigabytes that are being processed, things like that. And last but not least, I would expect that if I give away all those responsibilities from my own company or from my own team, I would expect that the solution is very highly available and secure by design and good integrated with the rest of the ecosystem. So how would that look like if we contrast that to the initial architecture that I've shown? So what we want to do, or in an ideal world, we only take our framework that we are using and the application code, and we hand that over to a service. And the examples will be based mainly on AWS Lambda today, but you can think about it as any other kind of serverless way of running the code. So, and the service then automatically handles like the capacity, the scaling, patching, and the administration of the infrastructure. So there are no servers or clusters involved sitting there idle, waiting for 24/7 or something. And I think one of the core value propositions is that the systems can scale to 0. So that means if I don't get any requests, essentially, I don't pay anything. Okay, so that means if I have an application that's being used from 8 a.m. to 5 p.m. and after that it's not being used anymore, actually everything will be scaled down to 0, and I'm not involved, and I don't need to pay the resources. I don't need to care about the resources actually. So, and scaling to 0 is a very interesting topic. So how can that actually be achieved? And so how can Lambda do that? And Lambda does that by running your code only in response to events. So you might be asking, okay, what is an event in that context? So an event can come from a variety of sources. So it can be from a change data, from a specific database. It can be an event, a traditional event from a messaging system. But we can also think about API requests as an event happening. So a user requesting, hey, give me all my orders, for example, we can treat that as an event. So, and based on that event, then the service would react, spin up, execute your functional logic, and afterwards spin down again. So I think that was enough of an intro about the theory and the concepts behind it and why would that be beneficial for developers or companies in general. So, and I want to show you now a bit on how that looks like in code. So here we see the integral part of a Lambda function. And that usually consists of three main parts. So the handler function itself that you can see, so that can be written from Java 8, 11, 17, 21 even, and it's basically just a simple Java function that you can think about. And then you're dealing with the event. So as I said, an event can come from a variety of sources. So usually those events look different if I react to something like a file was uploaded or to an API request. So depending on that, I get a different input event into my function. And on top of the event, I can also get something like a context object that contains additional information about the current request, things like a request ID, for example. So, and this is the only thing that you need to essentially write to in a serverless function or a Lambda function. So I mentioned that the events look different. So we have here open source libraries with all the POJOs from a variety of sources that can come into those functions. So you have the handler interfaces. So you just need to implement the interface essentially. You can use the POJOs and you would be good to go. You can, if you want, you can even leave that aside and deal with plain map to string, map of string to string, essentially attributes and handle it raw, but it makes your life easier. So usually you want to use the predefined interfaces. So I wrote my function and I know I know the integral parts of the function. So what is the next thing that I would need to do? So as we said, we're not dealing with servers anymore. So we're not defining like a specific instant time machine with that hard drive and so on and so forth. The only thing that we can configure now is the memory configuration. And everything like a CPU, for example, or network bandwidth will be aligned proportionally. So that means if I have a very high CPU intensive application, I wouldn't actually need to increase the memory configuration. That's how it works as of today. And so you might be asking, Okay, but how do I find that out, right? Usually I just give my container 8 gigabytes and I hope everything just works. And we have actually, this is an open source tool called Power Tuning. And this is very a good starting point for you because that would basically start your function in a variety of memory configurations and then give you a graph overview afterwards and saying this is the best configuration in terms of performance and cost, for example. And then you know what would be an ideal memory configuration that you might want to set. So we have written a function, or we know the basic elements of a function. We know the configuration that we need to set, only memory. And then last but not least, we need to package our app somehow and deploy it. So what are ways to do that? There are two common ways, and we will hear also about framework support a bit later. So the frameworks usually abstract that for you if you're using Spring, Micronaut, or Quarkus, for example. But if you'd want to do everything on your own, what you can build, one is an Uber jar, which is essentially a jar that contains all of its dependencies. Or you can also build a zip file with your class files and in a lib folder additional jars that you might need, like any kind of libraries or something like that. And when you have that, so you just have the Uber jar, your memory configuration, and then you just deploy it. You can do it manually in the console if you like, but you can also use things like Terraform or CDK or something like that. And then you would just upload that artifact, and that's it. Then you're basically, that was the whole responsibility that you needed to do. And initially, we talked a bit about events and the sources, and I want to give you a few examples what we see companies also building a lot. And to understand that, we first need to see also on different ways on how functions can be executed. And usually those are three ways. So I think the first one is the most common one. So a function can be invoked via an API like synchronous. So I get a request and then I do something and I return a synchronous response. So that's, I think, a very common approach. The second one is Lambda functions can also be invoked asynchronously. So that means, let's say I react to an event, something was uploaded to an S3 bucket or to any kind of file storage. And then, so that system says, okay, file was uploaded, but they are not really interested in getting any kind of response. So that means they just fire and forget the event, and Lambda makes sure to eventually process it, but it's not guaranteed like exactly when that will happen. We just know it will happen eventually. So that would be asynchronous invoke. And the third one, and I think this is a very interesting one if you're writing a lot of like streaming applications or messaging system, is that functions tend to have automatic integration within the ecosystem. So you could let a function automatically pull from a Kafka stream or from RabbitMQ or from SQS, for example, without you needing to write any kind of polling code, right, or any other kind of framework integrations that you usually see, where you need to see what is like the batch size and the container continuously run and pulls all the records. This is all directly integrated in those functions. So the function automatically for you processes the stream and continuous processing. And now I show you 3 examples of those to see a bit of code on how that look like. So I think the simplest one is like the synchronous one, so just some kind of thing that I want to return based on an API. And here you could use a direct URL. So usually you can function also across variety of providers, expose them via a URL directly. So you could deploy your function, that function gets an URL and you call it directly from your browser or Postman or whatever. And here you see the handling now. So you see that you get an HTTP event, which contains like the structure and headers and everything from the HTTP request. Then here, in that case, we just log something, we get the request ID, and then we return a response with that specific HTTP code, for example, and the proper and the body. So, and that's the only thing you need to write to have a full running REST API essentially in the cloud. So without needing to set up any clusters or whatever. If usually you don't only have like a single endpoint, but you're doing more complex things like routing, so you can integrate that with API gateways, for example, or other routing mechanisms to say if /unicorns is called, if it's the get method, please call this function. If it's the post method, please call the other function. And you would distinguish that by defining different entry points. You see them here highlighted in orange. So different classes with different handler methods on where to go depending on which path if you're building more complex applications. And the last example I think this is a very interesting one. As I will repeat myself, but I think it's very important because when we tend to write streaming applications or messaging system, as I said, we have this kind of polling mechanism. And here you see, for example, a function that handles items from a queue. And you see multiple instances here of that function. And what that means is Lambda will monitor the queue depth, so saying, okay, I have 50 requests, I will have just a single Lambda function processing that. Okay, but now I'm getting like a lot of requests to that queue. The queue is growing, growing, and growing. It will automatically scale up to 1,250 simultaneous Lambda functions processing the queue so that it can catch up. And this is already built in. You don't need a metric server or anything to monitor all of that or custom scaling policies. It's already out of the box, essentially processing of a queue. So here we already get a batch, so we get an SQS event, we get the records, we can then just extract the body from that records, for example, because usually you're not only getting a single item, but a batch of 10, for example. And then you can do some kind of processing, and even you could return a batch response saying, I was only able to actually process 8 out of 10 items, and then return like a partial failure, which is also quite convenient to do. So we talked a lot about events and how events come into the system, and there are certain additional points to consider when handling events, and especially when we're now looking more into the Spring ecosystem and Spring Boot, and Dennis will show you on how you can handle that most effectively.
Yeah, thank you, Max. So in the next part of this presentation, we dive a bit deeper on the event handling. So overall, what Max has already said, there may be synchronous requests like an API request. There may be asynchronous stuff like a file upload to S3. And we now want to understand what you need to do in the code. So inside the Lambda function where you write your code, you can basically execute all the code that you want to. You can call other AWS services. You can call other foreign APIs. You can access a database, for example. You can do whatever you can program in your Java code, right? But there's a difference in what you've done beforehand when you, for example, receive a servlet request in Tomcat, and also how you deal with the frameworks. And that is illustrated here. So on the left-hand side, you see the HTTP request that is coming in like you knew it before. For example, if you track it inside your browser or you use a curl command, it looks like that, right? You have the lines with a method, with a host header, and at the end you see a body with a payload. On the right-hand side, so after the API gateway, you see how it looks like when you receive it in your Lambda function, so in your function code. So and that's fundamentally different because now you have a JSON payload and a JSON structure, and somehow you need to deal with that, right? So, and as Max told you, there are some ways of using Pojo classes to just deserialize the JSON and process it based on that. And besides that, you can even also process it just in a raw format, like you take a map and you pull out the parameters from the map, or you use an input stream and you consume the input stream. That's possible, and there are also some libraries that offer support for that. So if you write a new Lambda function in Java, that's perfectly fine, but it may be not that convenient to rewrite the whole application, right? So yeah, we get to another method in a second. Just to tell you a bit more on how it looks like if you use a framework like Micronaut or Quarkus, or we have here as well Spring Cloud Function, which is another way of implementing it. And Spring, as those of you who know Spring always provides us some convenient abstractions, and we have the same for implementing serverless Java functions using Lambda, and also Lambda is one way of doing it. There are, of course, also other ways where you can run those functions. You see on top the typical Spring Boot application, and the only difference is here you have a functional interface, and what this function does, in the end it's the Spring Bean again. This function just converts the value to uppercase, so you get capital letters out of it. And that's all, and basically there's no boilerplate code around that, you just write this using the functional interface. And then you're done, you have implemented your function. So it's much more convenient, looks a bit nicer than dealing with JSON deserialization and pulling out things out of request objects. And in the end, it looks like that. So you have your application code in your function, and on top you have the Spring Cloud function framework that helps you dealing with everything else. So that's pretty nice because you have the abstraction, and it's easy to get started writing a new function. Unfortunately, we always have existing code, right? Sometimes we write new things, we may create new services, but we often have a lot of existing code that we somehow need to deal with. And what's common for APIs, for example, is a REST controller. So we have implemented REST controllers, we can just annotate them, and everyone who is at least working in the Spring field, and even if you're not using Spring, but rather JAX-RS or nowadays Jakarta RESTful Web Services, it reads like that. You have the method, it's somewhat annotated with a resource that you are trying to handle, and you don't want to rewrite all of this just to move the application somewhere else. Right? And maybe you also want the flexibility to just try Lambda functions, but if later on you notice there's so much going on, I want to move it back to a container because I have a continuous invocation, continuous load on it. That might be the case as well. So you want to abstract it. And this is another method. So instead of implementing it using the native functions, using the events, we can just plug in an HTTP adapter. So a component that helps us translating the events that I got from the outside world, the JSON payload, back to the old structure. Feels a bit weird because you are receiving HTTP via the API gateway, it's transformed to an event, and then we transform it back to an HTTP request. Why would we do that? Because most of the frameworks and our existing code, these frameworks, they understand the servlet request, for example. It's kind of a standard. We have it everywhere, and to reuse it, we build this adapter, and we can just leave the rest of our code as is. And one example is the AWS Serverless Java container. So we implemented an adapter as an open source project. It is on GitHub, and it provides you this kind of transformation layer. And today I'm very happy to announce release 2.0 of AWS Serverless Java container. So what I did this morning before coming here to JFocus is I started the release build finally. And some of you may wonder, why did it take so long to support the latest Spring Boot and the latest Jersey version? Yeah, it was a JavaX to Jakarta transition that some of you may have suffered as well, right? Maybe some of you, I see some heads nodding, are still on an older version. And if you are a library maintainer, you basically need to wait until all of your dependencies provide a version that is compatible with Jakarta EE as well. So that's why it took us a while to just transition it. We had 2 milestone releases last year already that were working. And what we've now included in the final release is also support for GraalVM native images. We dive a bit deeper later on. At this point, I'd also like to thank Oleg Zurakowski from the Spring team. So we made a collaborative effort out of this. Again, it's an open source project, so everyone can contribute. And what Oleg did from the Spring team is really provide a good integration between serverless Java container and the varieties of Spring there. So we work together with Spring Cloud Function as we've seen before. So there's basically, you can call it a plug or a delegation where we from Serverless Java container, we delegate it to Spring Cloud Function, and then Spring Cloud Function helps us integrating with Spring Boot or Spring Framework. But overall, the library also just works with a plain dispatcher servlet. So should you not be using Spring Boot, you can also just use it with Spring Framework. We are pretty flexible. That means you can just keep your code like Spring annotated with Spring Boot application and your controllers as is, and you just plug it in, you add the library, and then you are done. This is also just for the records here on the slide. We have a blog post linked here that describes it a bit, but the steps are pretty simple. You just add to your Maven or Gradle file, you add the dependency, then you configure a handler class. So Lambda needs to know what is the entry point, what's the class that I should call. You add it, you package it, you deploy it, and then you are done. If you want to do additional things, you can also implement your own handlers, extend it. As said, all the code is available on GitHub, so it's very easy to also take a look what's going on there. And you are very welcome to try it and provide feedback to us. So what are the advantages? Of course, so you can just easily port your existing applications with almost no code rewrite required. And some people even like the style. So some customers even create new applications like that because they are so familiar with the controller style because it's well established for them. So instead of doing the Spring Cloud Function way with the functional interface, they even write new controller classes. Aside Spring, so this was the whole example was now focused on Spring. You can also use alternative frameworks like Micronaut or Quarkus. There's also great support in there. You don't need Serverless Java container in this case. They directly implement that as well. So those are the possibility to get that running. So as a summary, the two ways that I've just explained. So the first one was handling via functions. So you consume the JSON payload and process it from there. This is almost a standard way if you are looking at non-HTTP use cases, like the example with the queue that Max explained. You wouldn't take the Serverless Java container and convert it back to HTTP because there's no HTTP involved beforehand as well, right? That's why for this use case, it's probably more useful to do it that way. The other way, on the right-hand side, the HTTP adapter is very good if you deal with HTTP APIs. If you already have some code in place that you don't want to rewrite, then it's just easy adding another library, just adding a layer on top, and you can achieve first results in having a serverless Java function running and try out some things and then use the optimizations. And speaking of optimizations, we will now look into performance and scaling of these functions.
Thank you, Dennis. All right, so I think we've heard already quite a lot. So we have easy ways to integrate it. We talked about scale to zero. We talked about scaling automatically, being in multiple availability zones. So everything sounds very good so far, right? And I would say never trust an architect that only talks about the positive things. So now we will look a bit into some of the challenges and some implications that the serverless way of doing things actually has. And for that, I want to dive with you deeper on how the scaling works of functional environments and how is that different to what we're used to. So what we're used to is like Java in a container or a VM. And how it works usually, so we pull the image and then our container will be initialized, so Spring Boot context, for example, starts up, and then we are dealing with requests or that long-running instances, so we can handle multiple concurrent requests at the same time because we have like thread pools and all that great stuff, and then the container just keeps running, and we only have that initialization in the very beginning, right? So that's quite a convenient way because whenever I get requests, the application is already there, and it can process it very fast. Now, in function environments, it works a bit different because I said we can get scale to 0, so there's nothing there, right? So there needs to happen something when we get the very first request. So how does that usually work? So let's say I get the first request and nothing is there, no environment whatsoever. So then what we do is we need to check if an execution environment is ready. So what is an execution environment? We haven't covered that, but your code needs to be executed somewhere. And how that is done is that under the hood, Lambda uses a firecracker micro VM, so a micro virtual machine, to run your code in an isolated way. And this needs to be created first. So what it does is, so if there is no execution environment ready, so we get the very first request, we create an execution environment. So we create that micro VM. And then we have to download your code, obviously, because it's your package lies somewhere. Then we need to start the runtime. So in that case, we start up a JVM. You can also use Python or JavaScript, whatever. And then we need to we initialize the function code. So what that means is we're calling any kind of static blocks or constructors. So those code needs to be executed first, and only then we can run the actual handler execution that we were showing before. And now you can imagine that takes quite, or can take quite some time, right? Code needs to be downloaded, JVM needs to be started, and so on. And all that is time that the request initially has to wait. So the very first call is usually quite, or can be quite slow. However, once we have an initialized execution environment for the next request, we can reuse that and just execute the code. And then it's very similar to what we are dealing with containers. There's, however, one caveat or one difference that you need to be aware of on what is a bit different. So when we go to, okay, maybe just one term because it comes up a lot of times. So the above is called a cold start. I'm not sure, you probably heard that term if you're in that space already, or a warm start. So if the execution environment is already there. Now there is another implication that makes the scaling a bit, let's say, tricky. Because so we said, let's go back to it. Let's say we get the first request. We say we need to create this execution environment. We do the initialization with all the things that I just explained. And then we execute your function code. Now that is cool. So if that has been done, we get the second request afterwards. We can just use that. So the caveat that I want to talk with you about is that whenever you get a request during a time where an execution environment is already doing some kind of work, either through initialization or execution, we would need to spin up another execution environment, and then that needs to be initialized again, and then we will execute your code because they're highly isolated from each other. So you need to be aware of that. So if you're getting a lot of concurrent requests at the same time, might be that only the first invoke is experiencing a cold start, but multiple of them. However, let's maybe find also something positive out of that concept, or maybe to conclude that diagram here, you see if the fourth request then come after the one was processed, we can reuse the first one. So when I have a certain amount of numbers of execution environments ready, usually I can process them very fast and reuse the existing one. So in an application where I get thousands of requests, right, after some times, usually I have enough execution environments ready and I don't need to worry about cold starts a lot. So really think about your P99 or P99.9 requirements if really cold starts are an issue for you. And one additional maybe advantage of that I want to make, so that means Lambda does handle the requests sequentially. So that means you never have to deal with any kind of concurrency in your code because you're at any point in time, your Java code and the JVM is only dealing with a single request. So which makes things like dealing with concurrent requests like a lot easier because you will always only get a single request at a time. So that might be convenient. So let's take an example, Spring Boot application. We use the serverless Java container. We put that on AWS Lambda, for example. And let's say you're using Java 8 even or something, and you're not doing any optimization. I can tell you it will take around 13 seconds for the first invoke. Now you would probably agree that for a synchronous REST API, a user sitting there 13 seconds with a spinning wheel is probably not the best thing to do. So there has been a lot of optimizations in the past on how you can optimize that. So the extreme case that I just talked about is on the left top with no optimization. Now there are a couple of optimizations you had to do manually in the past, like for example tiered compilation, which stops at level 1, for example, which is very good for faster startup, but a bit less optimal for if you're needing like longer cycles or for a very long running application, but usually we're dealing with very short-lived applications. So since Java 17 and 21 runtimes on AWS, we already have that enabled by default, and you would manually need to change it in the environment settings if you want to enable it again. So that means just by using 17 and 21, if you take that Spring Boot app, you deploy it to Lambda, you are at around 8 seconds, I would say. Still, 8 seconds for a synchronous REST call is not a very great thing to have. So can we do even more? So what you can think about also is thinking about lightweight dependencies in general. Do I need full-blown Hibernate implementation, or can I just use Spring Data JPA, for example, without all the Hibernate additional overhead that I might not need if I just have a single function, so you can reduce that even further. However, as we said, we have existing applications. We are leveraging maybe large libraries. I don't want now, just because I choose a serverless way of doing things, I don't want to re-architect my whole application, right? So are there other ways? And I want to highlight, or we want to highlight 3 parts that are below the 2 seconds or even 1 second mark, because that's, I think, the area where performance is acceptable again, even for cold starts for end users. And I think a more naive approach, or what you can think about, is the first one is provisioned concurrency. So that was the first kind of thing in the performance optimization that we did. So you could say, I know that I always get 10 requests at a time, for example. I want to always have 10 execution environments ready all the time. So what is the caveat there? Obviously, you also need to pay for them then there the whole time, right? You already pre-initialize them, they are there the whole time. Now, it does make sense if you have a very constant load and you know I always get 100 requests per second. It makes sense maybe to already spin that up, because the price actually that you would pay for an already existing environment, so just from the consumption method, would be cheaper. So if you have very predictable things, that might be not even to improve performance, but also for cost. But yeah, as I said, it's a bit then also the caveat that we initially talked about, that we actually don't want things running 24/7. So what do we do differently? And here 2 years ago, we announced AWS Lambda SnapStart. This is just for Java functions, because in Java, we usually tend to have those longer cold starts in comparison to interpreted languages, for example. So, and what it does is, if you are familiar, I'm not sure who of you is familiar with like snapshotting or CRaC. The CRaC project has heard about it at least. Okay, I will quickly reiterate on what we do here. So Lambda SnapStart takes a snapshot of your already initialized execution environment and the whole execution environment, so memory and disk. Okay, and then we encrypt that snapshot and we store it for low latency access later, so we cache it. And now, whenever you get the first call to your function, instead of spinning up everything again, we reuse that snapshot and we resume from the snapshot that we initially took. And this is fully managed, so you don't need to create any kind of snapshots files yourself. This is completely at no additional cost for Java functions if you're running on Lambda. So let's quickly walk through. I mean, I need to initially create some kind of snapshot, right, to be able to start from it. So what it does usually, during your deployment, we would spin up and create a new execution environment, execute all your code, static initializers as well as constructors. Then we take the snapshot and we store it. And then when the first request comes, we just resume the snapshot and then we execute your code. There are 2 points where we can add additional hooks. I will talk about that in a second. But to give you a rough idea on the existing Spring Boot application and what that implies is by using that snapshotting mechanism, you go down from 6.7 seconds has that example. That's a Spring Boot app writing to a Postgres database. So it's simple CRUD operation. Just by enabling SnapStart and getting that snapshot, you would be at around 1.15 seconds. So a huge difference for you. But as I said, every time things sound very good, right, there might also be things you need to consider. So in that case, and you might know that from the CRaC project, so what we are leveraging from the CRaC project is actually they provide interfaces to run things before the snapshot is taken and then basically after it is restored. So that might be if you have in your constructor, maybe you retrieve some form of credentials and they would be in the snapshot. So if your credentials change and you restore the snapshot, you might have outdated credentials. So with that hooks, you would use them to retrieve the new secrets, for example, right? Things like that. Things like invalidating existing network connections that might still be open. So, but all the major frameworks, right, are adding more and more of their own capabilities to those hooks. So for example, the Spring is also doing then a lot of effort there to shut down connections already for you so that you don't have to do all of that manually. So yeah, we're now at around that 1 second mark with SnapStart for existing Spring application. And now we will dive into custom runtimes, what those are and how they work together with GraalVM native image. And now you can accelerate that even further.
Yes, exactly. So just to recap how our current environment, so what we've been talking so far, how it looks like. So we have a runtime, a managed runtime managed by us, by AWS as a vendor, where we have the JDK in certain versions, 8, 11, 17, 21. And we take care of installing it, maintaining it. You just select the runtime version that you want to run on and provide your code, like we've seen, right? And there's an API in front of it, and we can provide, you can also use additional extensions to that. So now there's another possibility. You can decide you don't want the managed runtime, instead you want to provide your own runtime. So the runtime API is documented and you can just implement an own runtime, maybe even for some Java version that we are not providing a managed runtime for, or for GraalVM. So GraalVM recently became popular because it has a lower memory footprint and is overall the startup time is much faster. How does GraalVM achieve that? Some things that previously happened at runtime are just moved to the compile time phase. So who of you actually tried GraalVM compiling? Yeah, a few. What happened? It just takes longer, right, to build everything. And if you have an older machine, the fan goes on and consumes a lot of CPU because some of the work that the JVM does at runtime is just moved to the compile time phase, to say it in a simple way. And by doing so, you can achieve, as you see here, even with a changed memory configuration, you achieve very good results because even with very low memory configuration, the results are constant in here. So that's very compelling. And if you want to get the most out of it, GraalVM is probably a good option. The question is, do I need to take the effort to implement it on the left-hand side, right? You see there are more steps involved. It's not like before. I just provide my package with my application, uploaded it, and I'm done. I need to provide more. I need to add a bootstrap file that Lambda executes. I need to package it using a custom runtime on Linux. And it doesn't work with all of the frameworks and all of the applications. So there are some limitations like reflection or something like that. So that's something to watch out for. But depending on the requirements that you have, if you want to really get it down, and we've seen SnapStart with 1.2 seconds or something like that. With GraalVM, you can really go down to 500 milliseconds for the same use case, for example. So that's pretty good. Would I always say, yeah, this is the thing to watch out for, this is the thing to use? No, I think for many use cases, just enabling SnapStart is much simpler to get running. And most of the customers, for most of the use case, they are pretty happy with that. So you have a variety of options here, just to know both of them and maybe try it out depending on the use case that you are trying to implement. So now we've been to several options on how to implement it. It's not always easy to convey it in 50 minutes. So what we've also done is we are providing a deep dive, which is a step-by-step guide, which we have online. So you can just go there on your own and you find a step-by-step manual that you can click through and then you can try out the steps on your own. So that's available, and if you say, okay, yeah, that's still for me not sufficient, I want more support, we have solutions architects like ourselves available across the different countries, so you can just reach out to us, and we are also happy to run the workshop in your company with you, free of charge, of course. Just reach out, and we are happy to schedule something. Another helpful resource that we have is the Serverless Java replatforming guide. So overall, in serverless land, we have a lot of resources around serverless, and one of these resources is the Serverless Java replatforming guide, where you also find further guidance on what to watch out for when you take your existing application and try to replatform it. With that, we'd like to thank you. We have a few minutes left for questions now.
Yeah, hello. I wonder if SnapStart works in conjunction with a custom Docker image.
Currently, it's only supported for the managed Java runtimes that we talked about. So as soon as you're using a custom runtime, it currently would not work. Because it's also, if you have Python or anything else, it does not, it's currently only supported for the managed Java runtimes.
What are the prime candidates for using AWS Lambda?
The prime candidates, okay. So you mean like applications that are very relevant. So I've seen a variety of applications, so from basic APIs, as I said, there are different ways on how to invoke it. So we also see streaming use cases a lot because of the automated polling. So we see a variety of use cases that are very broad. I wouldn't specifically exclude a specific one. Sometimes if you have very predictable and very high load, very constant high load, just from a managed service perspective, right? Usually because we are doing a lot of heavy lifting with the service, right? And this is also what you pay for. But if you have a super constant load and not changing at all, sometimes just putting a container there just from because you don't need the flexibility of the scaling and all of that I talked about, right? If you don't need that, then sometimes container-based environments might be cheaper, and things like super performant computing, they need specialized hardware, then obviously that's also not a good use case for Lambda. I think that would be the rough. And for long-running jobs, for example, because Lambda, I didn't mention, has a timeout of 15 minutes. So if you have a job that runs, I don't know, half an hour, for very long-running applications, usually you would go with a container.
Yeah, like we also have a decision guide on our website, so we can also provide you with a link to that. That's sometimes helpful because it always depends on the workload, and within that decision guide, we try to quantify this. It depends in a way to what are the criteria to decide for one side or the other. Additional questions? Yeah.
Do you have any plans to add support for Ktor, Kotlin server equivalent? using Kotlin, or would you be open-minded to sort of like an open source contribution to support that server?
Yeah, thanks for the question. Currently, we have no plans, but we are happy if you open the feature request or even willing to implement something, that we would be very happy to accept the contribution. So overall, you have to understand that 90% of the things that we are building are basically based on customer feedback. So even if you, in one of the services or the frameworks, if you find something that you are missing and you think, in our company, this is the way it works, just reach out to us. We are happy to take the feedback and put it in our backlog. And the more customers come up with similar requirements, then the more likely is it that we will implement something. Okay, I think one last question.
Thank you. So a really short one. You mentioned the interpreted languages have a much shorter startup time. I was wondering if you have any insights of like how do the most popular languages compare in terms of startup to Java?
Yeah, that's a good question. There are a couple of open source repositories that have a lot of benchmarks between the different languages and the different runtimes. So I would suggest taking a look there. It's a very detailed look with different memory configurations, different languages. And yeah, that's I would say the recommendation I would give. I mean, typically there are, if you're doing things like Rust or something like that, right, or anything natively compiled, also like with GraalVM, for example, those tend to be just faster because just of how that works, right? How the language was designed, and yeah, it's. But I mean, what we see for those enterprise Java application and the ecosystem that has grown a lot, the current performance optimizations that we have, we can almost get on par to the other languages that also use like heavy, I don't know, HTTP frameworks or things like that. Yeah. So we are getting closer and closer. And I mean, the Java ecosystem has a lot of ongoing projects, right, to continuously improve the performance of the JVM in general. And I think we will just improve over time. As well, but I would guide to the benchmarks to see specifically per language on how they perform, because it's very different per workload and so on.
So now the very last question.
How would you handle JVM profiling and performance optimization of the code if it's running within a Lambda?
Yeah, that's a good question. There is a talk, I think 2 years ago also at DevOps Belgium that talks about JFR and how you would do that, for example, in a Lambda function. The thing is, we are dealing with ephemeral environments, right? And this is general a thing also in containers. If you're using managed servers also below, you don't have really access to sometimes the underlying, I don't know, like file system where you can just go SSH into it and then grab a dump or something out of it. I've seen implementations that are doing JFR dumps, for example, then on an S3 bucket, and then you download it from there then afterwards. There are a couple of examples out there, and we are also continuously improving our resources to add those additional, very detailed JVM statistics, for example. Okay.
All right, thank you. We are around here. Happy to meet you later on at the exhibition. Now it's time for a coffee break. Thank you so much for attending here.
Thank you very much.